Good morning. I want to go ahead and start to do a review over the sensitivity analysis. I don't think it's covered extremely well in the textbook, and so I pulled some information Dr. North had put together from another text that we used. And so let's just talk about the sensitivity analysis and how that relates to linear programming. Okay, so the objectives that we have is we want to be able to perform this analysis on a linear programming model and ask some questions about the relative impact of specific parameters in the model. Basically, at what point does the optimal solution that we've identified no longer make sense because of some changes that may take place? And so you can think about that in terms of whether or not, let's say we're trying to maximize profit. How much does a profit have to go up or down before our optimal solution would change? And the same thing in resources. How much would our resources need to increase or decrease before we would see a change in our optimal solution? You notice that in the resources, it talks about it as the right-hand side of the constraint. And that's typically because when you write a constraint, you say, let's say machine center A, machine center B. You would say for constraint for machine center A, and I'll go back to the example in the textbook, so many hours at machine center A. So let's see. I think we would say 4H plus 6C had to be less than or equal to 120. Well, that 120 is the right-hand side of the constraint, meaning how many hours are available of that. And then it says understand and interpret the shadow price of constraints as well as the allowable ranges of both the objective functions. Okay, so here's what we're going to do. We're going to keep moving through. So we're saying how sensitive are the results to parameter changes, to changes in the value of the objective function and changes, or the objective coefficients and changes in the right-hand side value of the constraint. You can do that with a trial and error approach or analytic post-optimality method. Okay, trial and error, it might take us quite a while to figure it out, so let's let Excel do it for us. Okay, so if we're going to do that, it's important to recognize that when we put parameters in our objective function, they're not always known with certainty. Usually they're just estimates, and those estimates don't reflect the degree of uncertainty. So after solving the problem, we can use these estimated values and determine how much those decision variables in the objective function would be affected if some of those parameters are changed, or we would do what's called a what-if analysis. Okay. Changes in the objective coefficients can be used to evaluate the impact of changes in price or cost. Again, usually our objective function is to minimize price or maximize profit, minimize cost, often used to answer questions by how much can we increase the price of product Q before our optimal solution changes. Okay. Optimal decision variables are only valid over a particular range, and we need to understand that range, and the sensitivity report allows us to do that. Okay. Now, you notice we switched topics from the objective function to resources. And so when we talk about resources, we're talking about shadow prices are often explained as answering the question, how much would you pay for one additional unit of a resource? And shadow prices are only valid over a particular range of changes in the right-hand side values. Okay, and so our sensitivity reports provides the upper and lower limits of this range. So just to, again, let's changes in objective coefficients. We're talking about the optimal decision variable values over a range, and in changes in resources, that's when we talk about shadow prices. Okay, and here's kind of when we print out our sensitivity report, we're going to find the information for reduced cost, the shadow price, the range of optimality, and the range of feasibility. Okay, and the reduced cost is how much the objective function coefficient of a decision variable must improve before the optimal solution changes and the decision variable enters the solution with some positive number. Okay, that only comes into play when you have a variable in the solution that comes back with a 0. Okay, the shadow price then is the marginal change in the objective function caused by a 1 unit change in the right-hand side value of a constraint. So for example, if my shadow price were $5 and I said on machine center A, an extra hour, if I were to pay overtime, was going to cost me $4, I would definitely say it would be worth it to do it, because it's going to change the objective function by $5 and only increase the cost by $4. Okay, the range of optimality is the interval of the objective function, which the optimal values of the decision variables remain unchanged. So optimality relates to the objective function, and feasibility relates to the constraints. Okay, and again, it's the boundaries of those constraints for which our solution will be valid for. Okay, so let's go ahead and look at an example. And in our example, we're going to talk about a manufacturing plant that wants to produce X-Pods or blueberries. Okay, and you can see that they're in electronics. It's 4 hours for each X-Pod, 3 hours for each blueberry. Our right-hand side constraint is 240 hours in the electronics department. Our assembly line takes 2 hours of X-Pods, 1 hour for each blueberry, and there's 100 available hours there. Our profit per unit is $7 for X-Pods and $5 for blueberries. Okay, so our decision variables are going to be X1 is how many X-Pods to produce, and X2 is going to be how many blueberries to produce. So if we were to set this up in Excel, this is what it would look like, right? We would have our objective coefficient of 7 and 5. We would have how many we were going to produce, right? And so if we take 7 times 30, it's 210, plus 5 times 40 is 200. So our objective function is 410. And we're going to max out on our left-hand side, or on our constraints, 240 hours of, what was it, electronics, and 100 hours of assembly. Okay? All right. Here is what our sensitivity report would look like. Okay? So our sensitivity report just, and let me show you in Excel. So let me escape from this and I'll bring up Excel real quick. So I had previously done the example in the textbook here, and so I can show you, if I wanted the sensitivity report, I would go to Data Solver, and when I finished solving, I would solve and it would say, do I want any of these reports? And I would say, yes, I want the sensitivity report, and it would come back then and add the sensitivity report for me. So now you can see here's my first sensitivity report, and there it is in Excel. Okay, so all we've done is run the sensitivity report and then shown you the outcome from that sensitivity report. Okay, and so that being said, all right, our final value was we would produce 30 X-Pods and 40 blueberries. Okay, our reduced cost doesn't come into play because neither one of these are at 0. Okay, our objective function was that we were at $7 of profit per X-Pod and $5 of profit for blueberry. Okay, the allowable increase says that this solution is viable, right, as long as the objective coefficient doesn't go greater than 10 or less than 470, excuse me, or more than 525 for blueberries. Okay, so it's 7 plus 3 is 10, 5 plus 0.25 is 525. So that's the range of allowable increase from 525 for blueberries up to $10 for X-Pods. Okay, the allowable decrease says 0.333, so it would be 7 minus 0.333, so 6.67. So my objective coefficient for X-Pods could range from 667 to $10 and still be valid. My objective coefficient for blueberries could range from 5 minus $1.50, which is $3.50, up to $5.25, and the solution that we have of 30 X-Pods and 40 blueberries would still be valid. Okay. Now we're going to look at the sensitivity report for constraints. Okay, and in that report, what we see is our final value was 240 in electronics and 100 hours in assembly. Okay, our shadow price is 1.5. Okay, and so if we recall, if we go back to shadow price, it's the marginal change in the objective function caused by a 1 unit change in the right-hand side value of the constraint. So what we would be saying is if I added 1 more unit to the electronics department, my objective function would increase by $1.50. Or another way of saying that is, as long as 1 additional unit costs me less than $1.50, I would be willing to add it to the number of hours available. If it costs me more than $1.50, it's not going to be worth my while. Okay, and again, we have a solution that says the right-hand side is currently at 240, and we can increase that by 60 units or decrease it by 40 units. So this solution is valid, this 30/40 solution is valid in a range of 200 hours to 300 hours. Or for the assembly line, it's valid for 80 to 120 hours because I'm adding the allowable increase and subtracting the allowable decrease. Okay, so that's how we read the sensitivity report. All right, so let's go ahead and scroll down here and let's look at a couple of examples. Okay, so what is the most we can charge for XPods? Okay, so we would say, what is the most that we can charge for XPods before the optimal solution changes? If this is done, how much can we expect to make? Okay, so XPods, the most that we can charge is $10 because it's 7 plus 3 times, so that's 10. So if we're going to do that, we can expect to make $300 on our XPods and $200 on our blueberries for a total of $500. Okay. All right. So the next question: what is the what is the impact on the objection function value if we acquire 10 more assembly hours? Okay. Well, if I add 10 more assembly hours, right? Assembly is here. The shadow price is 50 cents per unit. So 10 times 0.5 should give me an increase of $5 on the objective function. Okay. All right. The price of blueberries increases to $6. What is the optimal solution? Okay. So here I am. I'm going to look at blueberries. Okay. And it says, what if the price increases to $6? Well, it says this solution is only feasible up to $5.25. If it increases to $6, it's outside of the current solution, so we would have to resolve. So we don't know because it's beyond the allowable range that we currently have. Okay? So what we do know is it's no longer going to be 30,40 in terms of how many XPods and blueberries to produce. Okay? All right, so just kind of a look here. Remember, sensitivity analysis tells us how fragile or sensitive a solution is. The optimal solution of a linear program problem always occurs at a corner point. The feasible region of a linear programming problem is the area which simultaneously satisfies all of the model constraints. The shadow price is the marginal change in the objective function caused by a 1 unit change in the right-hand side value. These values are valid over a range of feasibility. A binding constraint is one where the left-hand side of a constraint equals the right-hand side of a constraint, or we have no surplus or slack. So I hope that helps you a little bit with your sensitivity analysis.